So now let us see what is CFSE formula. So if we know that T2G electrons have an energy of minus 0.4 delta O, we have discussed. EG have 0.6 delta O with a positive sign. And let's say the pairing energy is P. So number of electrons in T2G multiplied that energy plus number of electrons in EG multiplied that energy plus number of pairs into the pairing energy will be total crystal field stabilizing energy. We'll use that formula in the next frame. But right now, I'm telling you one very nice shortcut we can use for finding the strong field ligand. See, there's a spectrochemical series you should know, but in case in the exam simple hybridization question comes, you don't have to know the whole spectrochemical series. This trick will work. Trick is that when your carbon or nitrogen donor atoms are there, for any ligand, if carbon or nitrogen is the donor atom, it's a strong field ligand, otherwise it is a weak field ligand. One exception comes here, but it is not in your course, so it does not matter. Like azide is not a strong field ligand even though it has nitrogen donor. Otherwise, all of them will follow the same sequence. Let us see. So in CO, carbon is the donor, so it's a strong field ligand. In Cn-, carbon is the donor, it's a strong field ligand. In Nc-, nitrogen atom is the donor. Remember, in the ambidentate ligands, first letter is the donor atom. So carbon is a donor, strong field, nitrogen is a donor, strong field. In NH3, amine, only nitrogen is the donor, strong field. Ethylene diamine, amine again, so nitrogen is the donor atom, strong field ligand. NCS-, nitrogen is the donor atom, and SCN-, sulfur is the donor atom. See the brilliance of this part here. NCS- is a strong field ligand, but bhaiya, this is a weak field ligand. SCN- is a weak field ligand. Why? Because sulfur is the donor atom. So when nitrogen is donor atom, strong, sulfur donor atom, weak. Water, hydrogen is not the donor atom, oxygen is the donor atom. So again, weak field ligand. C2O4 2-, carbon is not donor atom, carbon have no electron in C2O4 2-. Oxygen is the donor atom. So bhaiya, this is also a weak field ligand. So that's a trick we can use for finding the strong field or weak field ligand. Next, let us consider this configuration. See, when we are finding hybridization of coordination number 6, we have two options. The options are D2sp3 or sp3d2. This D2sp3 is known as inner orbital complex, and this sp3d2 is known as outer orbital complex. So when we are using the outer orbital, it is called outer orbital complex. When we are using the inner orbital D in the hybridization, it is inner orbital complex. Understand, for complex compounds, for the hybridization, we need completely empty orbitals, because the ligand will give the lone pair. So you need completely empty orbital to keep those lone pairs. So understand here, for example, such a configuration is there. 3D, next is 4s, 4p, 4d. So 3d is the inner orbital, inner shell, penultimate shell, second last shell. Fourth is the last shell. So are any 2d orbitals empty in the 3d? Yes, there are 2d empty. So I will make D2sp3 hybridization here. 4d will not be required, and this kind of configuration, this kind of hybridization will give us D2sp3 inner orbital complex. Similarly, let us talk about this example. Here, any possibility of getting two empty boxes in the 3d orbital here? No, there is nothing empty here. Then you have to take 4s, 4p, sp3. So the option becomes sp3d2, and here the d orbitals that you have used is from the outer orbital, so we call it outer orbital complex. Please don't make any other hybridization like dsp3d or something, either d2sp3 or sp3d2. Please keep this in mind. Now going ahead, this is our spectrochemical series here. So understand, from here onwards up to the last, from here onwards till the last, these are considered as a strong field ligand. They are the strong field ligand, and I hope you can understand strong field ligand means delta O is more than P. Delta O is more than pairing energy, as we have discussed in the previous slide. Here in this case, these all are weak field ligand. That means delta O is less than pairing energy. That means in such a case, electron will jump up and will not pair because pairing requires more energy. In these cases, the electron will not jump because delta O is more, but pairing it will do because pairing energy is lesser. So strong field ligands are these, weak field ligands are water onwards. But one exceptional case comes here, keep this in mind. For cobalt 3 plus, only cobalt 3 plus, remember it's not for cobalt 2 plus, it is only cobalt 3 plus, nothing else, only cobalt 3 plus. Here onwards you have SFL. That means for everyone else, NCS minus to CO are the strong field ligand for every other central atom, any charge. But for CO3 plus only, oxalato onwards are the strong field ligand. That means EDTA 4 minus is a strong field ligand or weak field ligand for cobalt 3 plus, strong field ligand for everyone. But oxalato is a weak field ligand for others, but for cobalt 3 plus you have to consider it as a strong field ligand. So is F minus a strong field ligand for cobalt 3 plus or weak field? Bhaiya, it's a weak field ligand for cobalt 3 plus also. Understand, for cobalt 3 plus, just that C2O4 2 minus onwards became a strong field ligand, nothing else changed. And for remaining people, NCS minus onwards are the strong field ligand. Now I will go into the CFSE calculations and the hybridization questions for coordination number 6.